So moving on to our fourth skill in this chapter. This is called stoichiometry. And so stoichiometry problems, basically, as it says here, uses a balanced chemical equation to determine amounts of materials in a reaction. And the difficulty in these problems largely lies in how directly information is, again, given to you. If you're given quantities of materials in moles, it's pretty straightforward. And some of the earlier sample problems kind of stress this. This is a huge section. There's lots of sample problems. I've only chosen 3 kind of model problems to work through. But again, some of these other ones kind of in between here, or as we moved from 312, which is balancing equation, to 316 here, they have to do with some of the simpler versions where you're maybe given some information more directly. So I've kind of chosen 3 sample problems that kind of will represent good stoichiometry problems for us to practice. So again, as indicates here, we need to use a balanced chemical equation. So as we go through these problems, I will reinforce concepts that we talked about in our last sample problem on balancing chemical equations. Okay, so our next problem here, again, has to do with calculating quantities of reactants and products, and again, looking at mass to mass. So one of the other things that I will pull out here kind of to remind you of is this kind of, I've called this a mole game board, right? The idea is if we want to walk from a mass of one substance, or mass of a substance A, to mass of substance B, we can use molar mass to walk to amounts of that substance in moles. We can use the molar ratio from a balanced chemical equation to change who we're talking about. And then again, use a molar mass to reconvert from moles to mass, but now of a different substance. So this is essentially the walk that we're going to do here. That's our roadmap. But with this problem, we start a little bit further back because they don't give us a balanced chemical equation. They don't even give us chemical formulas. They give us words. So in terms of thinking about what we need to do here, we need to take these words and create formulas. So again, this mandates a proficiency in material learned in Chapter 2. Once we have those formulas, we can make a balanced chemical equation. Once we have our balanced chemical equation, then we're ready to do our math, our stoichiometry, again, our unit conversions. So unit conversions we introduced in Chapter 1, but we're practicing them with actual chemistry problems now. Again, using names to create chemical formulas we learned in Chapter 2, so we're going to stress that here. And we just practiced balancing equations. And again, balancing equations are really essential because that's what allows us to change between different substances that we're talking about. Okay, so let's implement that strategy with this problem. So this problem tells us during the roasting of copper 1 sulfide. So roasting means heating strongly with oxygen gas to produce powdered copper 1 oxide and gaseous sulfur dioxide. So they just kind of define what roasting means. They're defining it there. We want to know how many kilograms of oxygen, so oxygen's a reactant, are required to form 2.86 kilograms of copper 1 oxide. So copper 1 oxide is a product. But maybe we don't know that until we write a chemical equation. So let's first take and put these pieces of information together. So we've got copper 1 sulfide. So let's figure out what that is. Well, copper 1 is copper plus 1. Sulfide, and a lot of times people get confused. They'll write SO3 or SO4 for this. Sulfide, okay, is S2 minus. Sulfite is SO3 2 minus. And sulfate is SO4 2 minus. So again, proficiency in Chapter 2 and all of those names of those compounds is essential to being successful here. So copper 1 sulfide is going to be Cu2S. So Cu2S, right? We need to have 2 of those plus 1 cations to balance the S2 minus anion. So we've got Cu2S. Okay, so copper 1 sulfide. We're going to heat strongly with oxygen gas. So oxygen gas is this. Again, this guy was a solid. Oxygen gas, we're going to produce powdered copper 1 oxide. So you're going to have copper 1, and then oxide being in the same row of the periodic table, or I'm sorry, the same column of the periodic table as sulfur. It's going to be O2 minus. So again, we're going to have Cu2O, and again, that's going to be a solid. And gaseous sulfur dioxide. So sulfur dioxide, SO2. All right, so lots of pieces of information we had to get there from a name to create our formulas. So now we need to put these together in an equation and then balance it. So here again is our equation. We're going to have Cu2S, solid, reacting with O2, gas. And you'll notice I'm leaving some space here before each species so that I have room to put those coefficients that we'll balance with. Makes Cu2O, solid, and SO2, gas. Okay, so again with this, it's not like we have species other than oxygen that are represented in more than one species, so we'll leave oxygen to the end. And again, just like we saw in our last balancing problem, could potentially be a problem here because we have oxygen coming in as 2 atoms at a time, but we have a species here that basically shows oxygen coming 1 at a time. So let's go through and kind of try to balance this. Well, our coppers, we have 2 of them and 2 of them, so that's balanced. Sulfur, 1 of them and 1 of them. So every other atom is balanced now with the exception of oxygen. So I'm going to do the same thing we did in our balancing sample problem. I'm going to recognize that there's 3 oxygen in all of our reactant species here. And I've balanced every other atom, so that shouldn't be changing. If I put a 3 in front here, that's going to give me 6 oxygens on the left. So I'm going to recognize that oxygens come 2 at a time, and I'm going to say 3 halves. But what we need to do now is we need to scale up this currently balanced chemical equation, but that doesn't have whole number coefficients. So we scale this up, and we get 2 Cu2S plus 3 oxygens gives us 2 Cu2O plus SO2 gas, and again 2 of them. All right, going through them quickly, we've got 4 coppers, 4 coppers, 2 sulfurs, 2 sulfurs, 6 oxygens, 2 plus 4 is 6 oxygens. So we have our balanced chemical equations. We took our formulas, we made them into correct species here. We wrote an equation that we balanced, and now we're ready to do our math. So this is where I like to take information that's kind of provided in our chemical equation and kind of write it underneath here so it kind of makes sense. They tell us that we want to make 2.86 kilograms of copper 1 oxide. And so the question is, how many kilograms of oxygen are required for this? So again, a balanced chemical equation is a great way to kind of keep track of information that's provided and help us see the walk that we need to go between information that we know and where we want to go. So the roadmap here is again provided by your book, but I'm going to kind of keep consistent with how I like to write roadmaps. Take information that we know. I can go from this, I can go from mass of a substance to moles of a substance using my molar mass or my molecular weight. We're going to note here that we're going to have one more thing that we'll have to do because this is in kilograms. We can't go directly from kilograms to mole, but hopefully you guys will see that it's an easy unit conversion to go from kilograms to grams. We'll make sure to implement that when we actually act out our roadmap. So now we have moles of copper 2 oxide. We can use our balanced chemical equation to change who we're talking about. Go from moles of copper 2 oxide to moles of oxygen. And again, from this asks us to identify kilograms of oxygen. So to go to kilograms of oxygen to a mass, we'd need to again use our molar mass, our molecular weight. So hopefully this roadmap makes sense. What I'm going to do right now down below here is I'm going to implement that roadmap. So start with a piece of information you know. We've got 2.86 kilograms of copper 2 oxide that we want to make. Okay, now again, we need to not have kilograms, we need to convert that to grams, right? So again, I'm going to write down below here where we get these unit conversions. This is one of those prefix unit conversions, one of those that you needed to know. Okay, now we can use our molecular weight. 143.10 grams of copper 2 oxide is equal to 1 mole of copper 2 oxide. Again, this is a molecular weight or a molar mass. Now remember, I started talking before, when you're writing down quantities, and in chapter 1 we talked about the fact that quantities always have a value, a numerical value, and a unit. But as we work through stoichiometry problems, I'm going to specify that you should have 3. You're going to have a value, a unit, and an identifier. who does that quantity belong to? Because we want to make sure that when we're writing things, we don't miss a step. Okay, so again, our molecular weight will get us to moles of copper oxide. Now we need to use our balanced chemical equation to change who we're talking about. So we've got 2 moles of copper 2 oxide and then 3 moles of O2. So I get this information again from my balanced chemical equation. And these numbers just are the coefficients that appear in front of these species in the balanced chemical equation. So again, this is why it's important to have not only a value, a unit, and an identifier, because if I didn't have moles of this, I might think I'm ready to go in my next step to grams of oxygen. But we have to make sure we don't forget this, or we're going to be off by a factor of 1.5. Okay, so now I can take and I convert moles of oxygen into grams using the molar mass. So again, this is the molecular weight or the molar mass of oxygen. And again, the problem asks us how many kilograms of oxygen are required. So having this last step is important in order to answer the question. So we need to go back from grams to kilograms. And this is another prefix conversion. And so having that unit conversion is really important because it gets us to the answer that we're looking for. So 1, 2, 3, 4, 5 unit conversions that we needed to do our walk. A prefix, a molecular weight, an equation, another molecular weight, and a prefix. And again, this was our walk that we had here. Convince yourself that units cancel, kilograms cancel, grams cancel. And again, grams of copper oxide, moles of copper oxide. So moles of copper oxide to moles of O2, moles of O2 to grams, grams of O2, and then finally we're left with kilograms here. Rounded to 3 significant digits because we have 3 significant figures and the only value that they give us here. Remember, all of our molecular weights are going to have at least 4, if not 5 significant digits. They tend to have at least 1 significant digit after the decimal point, usually 4 significant digits total. So that's usually not going to be the limiting factor in our significant figures. So 3 significant figures gives us an answer of 0.959 kilograms of oxygen. So pretty involved problem, but again, stoichiometry problems are kind of a staple that we'll see in general chemistry.